Today we're diving deep into the fascinating world of microencapsulation, specifically focusing on interfacial polymerization and gellation mechanisms that create these tiny protective shells around active ingredients. Let me start by asking, what exactly are microcapsules? Microcapsules are tiny spherical shells, typically ranging from 1 to 1,000 micrometers in diameter, that encapsulate an active core material. Picture a tiny sphere with a protective shell surrounding a liquid or solid core. The shell acts as a barrier that controls the release of the core material. The core can contain virtually anything: pharmaceutical drugs, fragrances, flavors, vitamins, or even reactive catalysts that need protection from the environment. The shell serves two critical functions. It protects the core from environmental degradation like oxidation or moisture, and it controls the rate at which the core material is released. Now, how do we create these microcapsules? There are two primary methods we'll explore today: interfacial polymerization and interfacial gellation. Let's start with interfacial polymerization. This is a powerful technique where two reactive monomers meet at the interface of an emulsion droplet and polymerize to form a polymer shell. Imagine an oil droplet suspended in water. Monomer A is dissolved in the oil phase inside the droplet. Monomer B is dissolved in the surrounding water phase. When these two monomers meet at the oil-water interface, they undergo a rapid polymerization reaction, forming a thin polymer membrane right at the droplet surface. A classic example is the formation of polyamide or polyurea shells. Let's consider the polyurea system used in many commercial applications. An isocyanate monomer, Rn equals C equals O, reacts with a diamine, H2NR', to form a urea linkage, RNHCONHR'. Typically, the isocyanate is dissolved in the oil phase because it's hydrophobic, while the diamine is in the aqueous phase because it's water-soluble. The reaction occurs at the interface, and as more polymer forms, it creates a continuous shell that encapsulates the oil droplet. Now let's discuss interfacial gellation. This method is different because instead of covalent polymerization, we use ionic or physical crosslinking to form a gel shell. The most common system is sodium alginate, a natural polysaccharide cross-linked with calcium ions. This is widely used in food and pharmaceutical applications. Picture a droplet of alginate solution suspended in an oil phase. When calcium ions from the surrounding phase diffuse into the droplet surface, they cross-link the alginate chains. The negatively charged alginate chains bind with calcium 2+ ions to form a gel network through ionic cross-linking, creating what's called an egg box structure. This gel shell acts as a semi-permeable membrane that allows small molecules to pass through while retaining larger molecules inside the capsule. Now let's dive into the critical question: what controls shell formation? The answer lies in reaction kinetics and diffusion. These two processes compete and determine the final shell properties. Here's an important question: what determines how fast the shell forms? Is it the chemical reaction rate or the rate at which monomers reach the interface? The answer is both. The shell formation rate depends on whichever process is slower, the intrinsic reaction kinetics or the diffusion of reactants to the interface. To understand this competition, we use a dimensionless number called the Damköhler number, which compares the reaction rate to the diffusion rate. The Damköhler number equals K times C times L squared divided by D, where K is the reaction rate constant, C is the concentration, L is a characteristic length scale like droplet radius, and D is the diffusion coefficient. When the Damköhler number is much greater than 1, the reaction is fast compared to diffusion. We call this the diffusion-limited regime. When the Damköhler number is much less than 1, diffusion is fast but the reaction is slow. This is the reaction-limited regime. Let's explore the diffusion-limited regime first. This occurs when the reaction is very fast, so the shell thickness is controlled by how quickly monomers can diffuse to the reaction zone. In this regime, monomers must diffuse through the growing shell to reach the reaction zone. The shell grows slowly because diffusion through the polymer is the bottleneck. The shell thickness, h, grows proportionally to the square root of d times t, following Fick's law of diffusion. This square root dependence means that to double the shell thickness, you need to wait 4 times as long. This is characteristic of diffusion-controlled growth. Now let's consider the reaction-limited regime. Here, diffusion is fast, but the chemical reaction between monomers is slow. In this case, monomers quickly reach the interface but react slowly. The result is a thin, uniform shell that grows linearly with time. The shell thickness is proportional to K times C times T, where the growth rate is directly determined by the reaction rate constant. Linear growth means that doubling the time exactly doubles the shell thickness. This is fundamentally different from the square root dependence in diffusion control. Let's do a back-of-envelope calculation to estimate shell thickness. Consider a polyurea microcapsule with a 10 micrometer radius droplet. Let's set up our parameters. Droplet radius is 10 micrometers. The diamine concentration in water is 0.1 molar. The reaction rate constant K is 1,000 liters per mole per second, which is typical for isocyanate amine reactions. We have R equals 10 micrometers, C equals 0.1 molar, and K equals 10 to the 3 liters per mole per second. For small molecules diffusing through water, a typical diffusion coefficient is 10 to the minus 10 meters squared per second. D equals 10 to the minus 10 meters squared per second. First, let's calculate the Damköhler number to determine which regime we're in. dA equals KCl squared over D, which is 10 to the 3 times 0.1 times 10 to the minus 5 squared, all divided by 10 to the minus 10. Simplifying, we get dA equals 100. Since the Damköhler number is 100, which is much greater than 1, we're definitely in the diffusion-limited regime. The shell growth is controlled by diffusion. Let's estimate the shell thickness after 1 second of reaction time using the diffusion-limited growth equation. H approximately equals the square root of D times T, which is the square root of 10 to the minus 10 times 1, giving us 10 to the minus 5 meters. That's 10 micrometers. So after 1 second, we'd expect a shell thickness comparable to the droplet radius itself. This is actually quite thick. In practice, the reaction is stopped much earlier to achieve thinner shells, typically in the range of 100 nanometers to 1 micrometer. Now let's discuss shell permeability, which is crucial for controlling the release rate of the encapsulated material. Here's another important question. What factors control the permeability of the microcapsule shell? The answer involves 3 main factors: shell thickness, polymer density or porosity, and the degree of crosslinking in the polymer network. First, permeability decreases as shell thickness increases. A thicker barrier means molecules must diffuse a longer distance to escape. Permeability P is proportional to the diffusion coefficient D divided by the shell thickness H. Second, higher crosslink density reduces the free volume in the polymer network, making it harder for molecules to diffuse through. This dramatically decreases permeability. Imagine a highly cross-linked polymer network, where the chains are tightly connected. There's very little free space for molecules to squeeze through. Temperature also plays a crucial role. As temperature increases, polymer chains become more mobile, and diffusion coefficients increase exponentially following the Arrhenius equation. D equals D0 times e to the negative EA over RT, where EA is the activation energy for diffusion. Let's calculate the flux of a drug molecule diffusing out of a microcapsule. This is important for designing controlled release systems. We assume spherical geometry and steady-state diffusion, where the concentration gradient across the shell is constant. The total flux J equals 4 pi R1 R2 d delta C divided by R2 minus R1, where R1 is the inner radius, R2 is the outer radius, D is the diffusion coefficient in the shell, and delta C is the concentration difference. Let's plug in realistic numbers. Inner radius R1 equals 5 micrometers. Shell thickness equals 500 nanometers. So outer radius R2 equals 5.5 micrometers. R1 equals 5 micrometers. H equals 0.5 micrometers. R2 equals 5.5 micrometers. The drug concentration inside the capsule is 100 milligrams per milliliter, and outside it's essentially 0 as the drug is rapidly cleared. CN equals 100 milligrams per milliliter. C out equals 0. The diffusion coefficient of the drug through the polymer shell is much slower than in water, let's say 10 to the minus 14 meters squared per second. D shell equals 10 to the minus 14 meters squared per second. Now let's calculate the flux. J equals 4 pi times 5 times 10 to the minus 6 times 5.5 times 10 to the minus 6 times 10 to the minus 14 times 100, all divided by 0.5 times 10 to the minus 6. Simplifying, we get J approximately equals 7 times 10 to the minus 14 kilograms per second. This corresponds to about 6 nanograms per day. For a sustained release drug, this slow release rate is exactly what we want. Now let's discuss practical strategies for controlling shell thickness and permeability during manufacturing. Strategy 1. Adjust the monomer concentration. Higher monomer concentration in either phase leads to faster shell growth and potentially thicker shells. Strategy 2. Control the reaction time. Stop the reaction earlier for thinner shells or allow longer reaction times for thicker, less permeable shells. Strategy 3. Choose different polymer chemistries. Polyamides are generally less permeable than polyureas. Polyurethanes offer intermediate permeability. Strategy 4. Post-treatment and curing. Heat treatment or additional crosslinking after initial shell formation can reduce permeability by increasing crosslink density. Think of shell properties as a two-dimensional design space. You can independently control thickness and permeability to hit your target application requirements. Let me give you a real-world example. Fragrance encapsulation in laundry detergents. This is a billion-dollar application of interfacial polymerization. The goal is to protect volatile fragrance molecules during storage, survive the harsh washing environment, and then release slowly when you wear the clothes. The fragrance oil is encapsulated with a polyurea shell that's robust enough to survive washing, but permeable enough to allow gradual fragrance release over days. The shell thickness is typically 100 to 300 nanometers. This provides good mechanical strength while maintaining reasonable permeability. The capsules themselves are 5 to 50 micrometers in diameter, small enough to deposit on fabric fibers, but large enough to contain sufficient fragrance. For more sophisticated applications, we can create multilayer shells with different permeability in each layer. Imagine a core surrounded by an inner layer with high permeability for fast initial release and an outer layer with low permeability for sustained release. This creates a biphasic release profile. Each layer can be formed sequentially by changing the reaction conditions or introducing new monomers after the first layer has formed. This enables complex release kinetics, such as an initial burst release followed by sustained zero-order release over weeks. How do we measure shell thickness and permeability experimentally? Several techniques are available. Scanning electron microscopy, or SEM, is the gold standard for measuring shell thickness. You fracture the capsules and directly observe the shell cross-section. Transmission electron microscopy provides even higher resolution for examining nanoscale shell structure and detecting defects. Permeability is typically measured indirectly through release kinetic studies, where you monitor the concentration of released material over time. The release rate dm over dt equals permeability P times surface area A times concentration difference delta C. Atomic force microscopy can probe the mechanical properties of individual capsules, measuring shell stiffness and elasticity. Let's discuss some common challenges in microencapsulation and how to address them. Challenge 1. Shell defects and pinholes. Even tiny defects can dramatically increase permeability and cause premature release. Solution. Optimize the emulsification step to create uniform droplets, and use a slight excess of one reactant to ensure complete coverage. Challenge 2. Capsule aggregation. If capsules stick together, they can't function properly. Solution. Add stabilizers like surfactants or polymeric dispersants, and control the ionic strength of the continuous phase. Challenge 3. What works in the lab doesn't always scale up easily to industrial production. Solution. Transition from batch to continuous flow reactors, which provide better control over mixing and reaction time at large scale. The field is moving towards smart microcapsules with stimuli-responsive shells that release on demand. For example, pH-responsive shells that dissolve in specific pH ranges enable targeted drug delivery in different parts of the gastrointestinal tract. Temperature-responsive polymers like poly-N-isopropyl acrylamide undergo phase transitions at body temperature, enabling heat-triggered release. Enzyme-degradable shells can respond to specific biological signals, releasing their payload only in diseased tissue where certain enzymes are overexpressed. Let me summarize the key concepts we've covered today. Interfacial polymerization and gellation create protective shells right at the interface between two immiscible phases. The Damköhler number tells us whether shell growth is limited by diffusion or by reaction kinetics. In the diffusion-limited regime, shell thickness grows proportionally to the square root of time, while in reaction-limited conditions it grows linearly with time. Shell permeability is controlled by three main factors: shell thickness, polymer cross-link density, and temperature. We can tune shell properties through monomer concentration, reaction time, polymer chemistry, and post-treatment methods. These techniques enable applications from controlled drug delivery to fragrance encapsulation to protecting sensitive catalysts. The future of microencapsulation lies in creating smart, stimuli-responsive systems that release their contents on demand in response to specific triggers,